Welcome to part 6 of my online probability course, Math 3350, Probability and Statistics. Today we're going to be talking about using partitions. Now, partitions are a group of subsets that completely cover a probability space, and they have some important properties. Okay, so we have these collection of subsets, and none of them is empty. So every single one of the subsets has something in it. The subsets are all pairwise disjoint. That means that any one element is going to be either in A sub 1 or in A sub 2, but not in both, right? We can't have any elements that are in two of the subsets. And finally, the third requirement is that the union of the subsets is equal to the entire probability space. That's what I mean by the collection of subsets covers S, right? Every single outcome in the probability space S can be found somewhere in the collection. Now, these are really powerful tools for calculating probabilities because it allows us to break down complicated events into baby steps, right? We can work inside the subsets of the partition on more granular problems and then just multiply all of our outcomes together to get a final result. And we're going to look at an example right now to see how that works. So this is a chessboard. Now, normally bishops are light square or dark square bishops. And this particular problem says, hey, we're going to slap 3 bishops down on the chessboard somewhere. We're going to pick some squares. Boom, boom. We're going to pick some squares at random, and the question is, what is the probability that all 3 bishops land on the same color complex? Either they all land on light squares or they all end up on dark squares. Let's think about this partition that we have. We have this ready-made partition existing in the problem because there are 32 of the 64 squares on the chessboard are light squares, and the other half, the other 32, are dark squares. So we have a 2-subset partition. We have the subset of light squares and the subset of dark squares. So here's what we can do. We can use this partition just to pick whether we're going to have a light square or a dark square. So ignoring for the moment, actually, let's talk about picking at the partition level. So this probability, let's just write it down. So the probability of them landing on the same color, I'll just kind of write the probability event, a shorthand for the probability event inside the parentheses. That's fairly standard. Is going to be what? It's going to be 2 choose 1 times 32 choose 3, and the probability space will, from all 64 squares, we'll choose 3 of them to have bishops on them. Okay, so let's explain these top items here. What does the 2 choose 1? Well, the 2 choose 1 picks between the light squares and the dark squares, right? So there are 2 choose 1 ways to pick one of the subsets of the partition. Once we've selected it, let's just say that it was the dark square partition that was selected, right? Then there are 32 choose 3 ways to pick elements from that subset to have bishops on them, right? So that's what we mean by using partitions. The first pick in the numerator is a partition level pick. Picking which of the subsets is going to become active, right? Where we're going to get our choices. And then the second one actually picks the square, right? The 3 squares where the bishops are going are chosen in this second choose notation. And then, of course, the denominator, I hope by now in the course, the denominator is self-explanatory. We have 64 squares we could put 3 bishops on, so 64 choose 3 is the correct denominator. I'll pull up the graphing calculator just to get you some more familiarity with how these work. So I'm going to take 2 choose 1 is just 2 times 32. Then I'm going to math the probability menu, and then NCR is the third option. So 32 choose 3 divided by, and then 64. math probability, choose 3. And remember, this behaves like a parentheses, right? The NCR is a function that these numbers go into, and it's not going to do the 3 divided by 64. It's going to take this whole 64 choose 3 as a single quantity when we hit execute. By the way, I didn't show this last time, but you can hit math and then arrow frac, and it will convert it to a fraction in lowest terms. So we can come back over to the problem and write 5/21 as our probability. So remember that arrow frac, it was here on the math button. The very first option on the math button will switch into a fraction form. And it will always reduce a fraction. So if you have something that's non-reduced, this helps. So a couple of pro tips there with the calculator. If you try to think about other ways to solve this problem, you'll understand why the partitions are so powerful. So let's just go in order. Let's slap a bishop down, okay? So suppose we slap a bishop down on this light square here. Well, so if I'm trying to build out a probability tree, the probability that something lands next to it is very different out here in the middle than it is if it gets put in a corner, which is even different than if it gets put here on an edge. So I have 3 different configurations of whether I have only 3 spaces adjacent to it, or whether I have 5 spaces adjacent to it, or whether I have 8 spaces adjacent to it. So these probabilities, if I tried to place a bishop and then calculate the probability of another bishop being on the same color square, right? I mean, you'd have to, the counting is going to get really crazy. Yet we use the partition of the subsets into light squares and dark squares, and it really simplifies the way that we're working. So this is a really powerful tool, and hopefully the next few examples will further explain why. Now I put all of the notes here. I left them in on your notes pages. Let's talk about these calculations, and you may want to make some additional notes, but I think this is really important. I wanted you to have access to all of the rationale. And you may even want to pause the video and make sure you understand it if there are a couple little notes you want to jot along the way. But if you can get the next 10 minutes of this video, if you can understand it, you'll be doing extremely well for the rest of the course. Okay, so now we're going to talk about 4 of a kind. So we have a 5-card poker hand that we're drawing cards into, and we want 4 of them to be the same, like ace, 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 ace. That would be a great 4 of a kind to have. And we're going to have the event set 4K. All right, and then let's talk about why this works. What are we doing here? So this is a partition level pick. From the value partition, right? The value partition has the 13 values, ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, right? Those are the 13 values. And so from those 13 values, we're going to pick one. And this one right here, the one that we've picked, is going to be the value of our 4 of a kind, okay? And then we pick the cards that go into our hand from that value partition. If it's 8s, let's say, there are 4 8s, and we have to have all 4 of them land in our hand. So these 4 are the ones that are actually going into our hand. Then 12 choose 1, what's that? Well, from the remaining 12 values that weren't in our hand, we have to pick one more. One more value is going to be in our hand. If we had 4 8s, then we might have something like a 3. 4 8s and a 3. So this is picking from the remaining 12 value subsets. It's going to pick one. So this is another partition level pick. And then this goes inside that partition. Let's say it's the 3s, and it picks one of those 4 3s to be in our hand. So you've got partition level pick, then you pick the cards, then you have another partition level pick, and then you pick the cards. And so I have these written out, right? 13 choose 1 is a partition level pick. Then pick all 4 of the 4 of a kind cards. Partition level again, 12 choose 1, and then pick one of the 4 cards. By the way, we do not necessarily need to do 12 choose 1 times 4 choose 1. One other way to look at these right here is as 48 choose 1, right? In other words, I've gone inside one of my value partitions. There are 12 value partitions with 4 cards in, and there are 48 cards left, right, that haven't been picked from yet and haven't been picked yet. So I can do a 48, oops, I can do a 48 choose 1 instead of the 12 choose 1 times 4 choose 1. Anything choose 1 is just that number, so 12 choose 1 is 12, 4 choose 1 is 4, so 12 times 4 is 48, 48 choose 1 is 48. So these here in red are equivalent. So I could have done that either way. I just thought I'd show you about, yes, we're doing a partition level pick, and we can do a partition level pick again for the second card. And sometimes that'll be important. You'll see in later examples when that's important. So let's take a look at having a one pair hand. Now, there's a little nuance here. The question specifies exactly one pair. And let's talk about why. Because I could have a pair of kings, let's say, but I could also in the same hand have a pair of queens. So if I'm not careful about how I pick the remaining cards after I've picked the pair, right, this is actually, this term here is the one that's picking the pair. The cards that are in the pair that actually go into my hand are picked in that second binomial coefficient term there, 4 choose 2. After that, I have to make sure that I don't end up with any more of the same value, right? If I have a pair of kings that gets picked, I can't have any more kings, but I'm okay to have a queen, but I couldn't have a second queen get picked. So I'm going to have to take care of that. So let's think about how these partition picks are working, right? So partition level, this first 13 choose 1 is a partition level pick. And out of all 13 possible values, it picks one that's going to be my pair. The pair value is right here. So this has picked the pair value at the partition level. This has gone inside the subset and picked the actual 2 cards of the pair that end up in my hands. Then the 12 choose 3 goes back to the partition level. And let's talk about this. This is interesting. 12 choose 3, so we're picking 3 more values. This is going to make sure that none of the values are the same. In other words, I can't have a queen and then a queen. This is a situation where we definitely don't want to do something crazy like just going 48 choose 3. Right? If I just use 48 choose 3, then I could get 3 queens. I could end up with a full house, or I could end up with 2 8s. So that's definitely not the way to go. What this will do for us if we use this partition level pick here, this 12 choose 3, gets me 3 different values. And because 12, I'm using 12, I'm ignoring the one that got chosen here, right? So from the 12 remaining subsets that didn't get picked here, I'm picking 3 of them. Now, each one of these 4 choose 1 cubed binomial coefficients, each one of these terms is going inside a value and picking one of the 4 possible cards. So this is 4 times 4 times 4. This is actually equal to 64. The 4 choose 1 cubed is equal to 64. Okay. Now, why? There's another question here. If you're thinking clearly, you'll be asking yourself, well, why couldn't I have picked 4 cards, 4 values at the partition level at the very outset, right? Just pick all 4 of them at once. Pick the 1 I need here and pick the 3 I need here. Well, that's one of that's a nuance. That's a tricky thing about the partition level pick, right? That when the cards are chosen at once, right? When I do 12 choose 3, they need to be serving equivalent functions, right? So these are just the 1 card singleton values sitting by themselves, so they can all be picked at once. But they serve a different function than this one over here, which is picking the pair. So that's why we have to do 2 partition level picks. That's why 13 choose 4 doesn't work. It would end up overcounting these different, we would count too many. All right, so let's take a look at, oh, sorry, I didn't show that part of the slide, but yes, the 4 choose 3 is the last card level pick. So let's look at 3 of a kind, and this should be pretty straightforward reasoning, right? We have a partition level pick that's choosing the value for our 3 of our kind, then we pick the 3 cards out of the 4 from that value, and then we're going to return to a partition level pick to pick these 2 singleton cards. Again, I can't do 13 choose 3 and pick all of the partition cards at the same time because they serve different purposes, right? I'm going to have 3 of these guys, but only 1 each of these. So these 2 values have to be picked later. Okay, and then 4 choose 1 2, again, that's going inside my hand for the final pick. So the 4 choose 3 is at the card level, picks 3 cards to be in my hand. 12 choose chew is back at the partition level, figuring out which values are going to be in my hand. And then the 4 choose 1 squared, that's going back in and getting the last 2 cards to be in my hand. So I hope this is starting to make sense. These partitions are really powerful, and these poker hands are really a great way to learn. By the way, you can do these as probabilities. The number of 5-card poker hands is just 52 choose 5, which is somewhere around 2.7 million, I think. Is it 2.3 million or 2.7 million-ish? So any of these could be turned into probabilities by dividing the number we get when we multiply these out by 52 choose 5. I wanted to simplify it and look in terms of cardinality of sets, just how many elements, how many outcomes are there in these sets, because I just wanted to think about the partitions and how we're using the partitions to pick the different cards in our hands. So I wanted it to be as simple as possible. So I made them counting problems instead of probability, but we can do the probability questions very easily. So with 2-pair, we are going to start picking at the partition level. And because we have 2 pairs, they're going to be serving exactly the same function, right? When I do 13 choose 2, both values I'm picking are going to have 2 cards chosen that go into my hand. So they'll get picked all at once. So this first partition level pick, 13 choose 2, gets me the pairs. Then the 4 choose 2 squared, that goes into each of those 2 values and grabs me 2 cards. So now I have 4 cards in my hand after this 4 choose 2 squared. Then I go and out of the 11 remaining partition level values that haven't been picked yet, we pick one of them, and then from there we get one of the 4 cards there to go into our hand. By the way, it would be okay to do 44 choose 1 here. All right, because there's no danger of getting a pair here, right? We're only picking 1 card. So if I'm only picking 1 card, 44 choose 1 instead of doing the partition level pick and then the card level pick is fine. Okay. Now, the question is, why is this wrong? Okay, let's take a look at what the difference is here. We have 13 choose 1 times 4 choose 2, right? So 13 choose 1, we get this card in our hand, and then, we get this value, and then we get 2 of those cards in our hand, and then we pick this value and get these 2 cards in our hand. And then this is just the same at the end, right? This part hasn't changed. The answer is, why is it wrong? And this is double counted. Let me see if I can explain why. So when I pick 13 choose 1 and then 12 choose 1, I'm saying that they're serving different purposes. What I'm saying is that a hand like, let's say my 2-pair was queen, queen, 7, 7. Okay, if I count like this rather than like we did up here, then I'm saying these are 2 different hands. That 7, 7, queen, queen, right? That if I have that the queens and the 7s have a different job, right? If they have a different job, then we're going to count them twice. Well, this is the same hand. It doesn't matter which order the pairs come into my hand. So this actually counts 2 times as many as we need. And this is the correct way to do it. Again, with partition level picks, when the values that I'm picking are going to serve the same function, then they have to get chosen together. Okay, and the final example we have here is the full houses. Okay, so a full house is a hand like Jack, 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 6, 6, right? Where I have 3 of one kind and a pair in the same hand. Okay, so how's that going to work? Well, think about the partition. Why are we starting with 13 choose 1? Because the 3 of a kind that I'm choosing serves a different function than the pair that I'm choosing. So since these 2 partition level picks are picking things that serve different functions, we have to separate them and do them at different times. Okay, so 13 choose 1 is partition level pick. We're picking the value for the 3 of a kind. By the way, it wouldn't matter if we swapped the 4 choose 3 and the 4 choose 2. What matters is that the partition level picks are separated so that we know that the two things are serving a different purpose. We can just swap, these two terms and we have the same value, right? We were counting the exact same way. So, but here I just said, well, let's pick the 3 of a kind first. And at the card level, then we go into the subset and say it was jacks, right? We go in, of the 4 jacks, we pick 3 of them. These 3 actually go into our poker hand, right? Then the partition level pick 12 choose 1. So from any of the 12 remaining values, pick a value for the pair. And then inside that, we're going to pick 2 of those cards. So where I've circled, those are where we're getting the 5 cards that actually go into our hand. Okay. So let's ask this question, sorry. Why won't this work? And I hope you've got it figured out. The 13 choose 2, the partitioning is not working. So here we sort of have the opposite problem as we had before. Here, when we pick 13 choose 2, we're saying that they serve the exact same function. So now what we're saying, if we have jack, 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 4, and 4, right? That hand, we're saying that that's exactly the same as 4, 4, 4, jack, jack. Sorry. Right, well, these are obviously not the same, right? So here we've undercounted. When we use the partition level pick to pick 2 things, they have to be serving the same purpose. And obviously the jack value and the 4 value are very different. It matters whether it's the 3 of a kind. This is a much better hand than the 4s. By the way, for poker players, they would say that the top one here is jacks full of 4s, and the bottom one would be 4s full of jacks. And that's how they distinguish which is the 3 of a kind and which is the 2. So I hope you can see the power and the usefulness of partitions. They really simplify the actual picks that I'm making. I mean, think about this, right? I'm just like, oh, how many values are going to be in my hand? Well, 2 of them. Okay, well, let's pick. Now, again, this was wrong, so maybe I should roll back up here, right? Let's go in and let's pick a 3 of a kind from our 13 values. Pick a value to be the 3 of a kind and pick a value to be the 2, the pair, the 2 of a kind. And then I go inside that value, pick my 3 cards that I need for my 3 of a kind, go inside where the pair value is, grab those 2, and when I've picked all my cards, I'm done. So we have a very intuitive and powerful process where we use these partitions and their subsets to make probability problem solving much easier. So definitely consider watching this one again. If you can do this well and understand why you're using a partition level pick and why you're using a card level pick at all times, you're going to be well on your way to doing very well in this course. Remember to do your content quiz and have a great day.